Alright, y'all. Welcome to the last part of week 12 problem 2. I know we have gone so far on this, but let's end it beautifully, okay? So for part D, they ask you to derive an expression for PA minus PP. And this term right here is also called the pressure drop. Pressure drop. You know, for fluid mechanics and transport people, pressure drop is a very interesting term, and everyone is very focused and interested in obtaining the value of pressure drop. You can tell a lot about how good the transport is and how efficient the transport is. Okay, so in order to derive an expression for the pressure drop, you need to draw a picture, okay, using force balance. So I write using force balance. Okay, so we have what? We have a tube, right? We have PA coming in this way. We have PP coming out this way. And we have shear stress is opposite to the direction of the flow, and this is length L, and this is diameter D, small d. Okay, so how do we do this? You can use a force balance. You can say force exerted by pressure drop equal to force exerted by wall stress. Okay, so what can you get? You get PA minus PB times cross-sectional area equal to surface area times the average shear stress. In this case, we use average shear stress. I guess because of the unit, because it's per length, so you make sure the unit is correct. But that is my best bet for these problems. Okay. So what is the cross-sectional area? Again, our tube, the cross-sectional area is the area of a circle, so it's pi d squared over 4. That d is diameters. The surface area, again, shear stress only acts on the surface area. The surface area for the cylinder is pi dl times tau w. Okay, so we can solve for PA minus PP is equal to pi dl times w over 4 pi d squared over 4. So this equal to, I'll put 4 up, so 4 pi dl tau w over pi d squared. What term can we cancel out? We can cancel the pi out, d out, so it become d. So this becomes 4 times L times average shear stress over D. Y'all remember from part C, we derived an expression for the average shear stress already. Okay, again, just the tail part, just like part B. So we have this term right here in green, tau W over 1/2 rho Vx is infinity square. We get it as a function of the Reynolds number, right? We get it, yeah, right here, 8 over square root of 30 and square root of REL. So let's go ahead and use that. So if you want to use that, you have to make sure that, so average tau mu over 1/2 rho Vx infinity square. This term appear, and you have to return it by time it. Divide by a number, times it by the same number to return. Okay, so let's go ahead and simplify it. So it's 2L rho Vx infinity squared times average shear stress over rho, sorry, 1/2 rho Vx infinity square over D, right? So we have this term already, y'all recall. Let me write. Recall from part C. So we get 2L rho Vx infinity square times square root 8 over square root 30 over square root REL, right, over D. For to simplify it, I will simplify it further. Highlight this so y'all understand. So 2L, okay, let me write this way. Okay, so it should be 16L rho Vx infinity square over square root 30 times square root of REL times D, right? Okay, wonderful. What is square root of REL? Reynolds number with respect to L, you get 16 times L times rho Vx infinity square over square root of 30 times square root of rho Vx infinity times L over mu times D, right? So the question is, can we simplify this further? Let's see. Yes, we can, I think. I have to make sure everything is correct. Yes, we can. Okay. So I'll introduce the ego to this this problems. Okay, we do it step by step. We get there. Okay, you just need to have faith. Faith is very, 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 very important now. So okay, I will introduce something. Y'all ready? 3, 2, 1. Okay, I will introduce the term veta. So let me use breath. Introduce veta. So this veta right here, like a bird. So it is called kinematic. Sorry, not kinetic. You take a kinetic class, but not now. Later. It's called kinematic viscosity. So it is defined as what? So veta is equal to mu over rho. So our mu is absolute or dynamic viscosity. So rho in this case, the density of the fluid. Okay, so we're gonna introduce this term to our equation. So veta equal mu over rho. So rho over mu is 1 over veta. So I will highlight these. So I'm gonna introduce this in. So you get this equal to 16L rho Vx infinity square over square root of 30 times square root of Vx infinity times L over veta times D. So let's go ahead and make it look nice. So it's 16. Since square root of veta is in the denominator, I can put it up. So or you can say times both denominator and numerator for square root of veta. So you get 16 times square root of veta times L times rho times Vx infinity square over square root of 30 times square root of Vx infinity times square root of L times D. Okay, what can we simplify? square root of L, and square root of L is gone. So this becomes square root L. Okay. Okay, so recall, you know that Vx infinity square is square root of Vx infinity to the power of 4, right? So if this one right here, if you divide by square root of Vx infinity, you get square root of Vx infinity to the power of 3. So what does it mean? It means that this term right here cancel out, and this becomes square root of Vx infinity cubed. Okay, can we do anything further? No, we cannot. So let's simplify it. You get 16 over square root of 30 times d times square root of beta times L times Vx infinity cube. Alright. Did we miss? I missed a row. I'm so sorry. So we use a row right there to make sure. Okay. And if you want to get a numerical value, 16 over square root of 30 is approximately 2.92 times rho over d times square root of beta times L times Vx infinity cube. And ladies and gentlemen, this is our expression. So now you can compute the pressure drop directly, just knowing the density of the fluid rho, the diameters of your tube, the absolute velocity, the atmospheric velocity, or the fluid constant velocity. I need to check that, the length of our tube, and the kinematic viscosity. I hope this helped, and I appreciate y'all stay tuned from the beginning to the complete end of problem 2. I hope you have an amazing day. Thank you.